week there was a lot of, I guess you could say, like kind of theory and fundamental understandings of high privacy, what are privacy enhancing technologies, and really kind of getting our heads around, you know, some of the basics, reasons for it, the needs for it in the context of UNHCR, but also the broader UN and national statistics organizations around the world. And then kind of an introduction to both input and output privacy and a bit of a deep dive on differential privacy, simply because by participating in the competition, you have to really kind of get your head around differential privacy as well, because the privacy kind of metrics, your epsilon and deltas, kind of work towards your ultimate score, which we'll go through in a few minutes. But this week, we have each of the differential privacy frameworks, as well as the input privacy technique that we're using, which is around secure enclaves. And we have speakers, most of which have actually written the frameworks mostly themselves. So some of them, I think, wrote it completely themselves, some of it with a broader team, etc. So if you have any questions, definitely ask them, and you can actually kind of hear from the horse's mouth, you know, their thoughts or, you know, opinions, etc. on the frameworks, maybe limitations, maybe advice if you're using them in the competition, etc. And yeah, and hopefully this is quite a practical kind of hands-on type session. And following this webinar, a little bit later in the week, there will also be a GitHub made available to everyone, which allows you to basically get your hands dirty with each of the frameworks, etc., and have dry runs of how you would use them in the competition. And you can use that basically anytime up until the competition itself. And there's also starter code for the competition itself. So it's kind of a one-stop shop for everything that you need to participate in the competition. However, hopefully these talks give context and additional information that will kind of set you up well for them. So I'll kick it off myself, and then we're going to pass over to a number of the speakers who we have with us today. So great. So I just wanted to kind of recap of some of the types of things we try to do within the UN Pet Lab, but even more broadly within the community of privacy enhancing technologies. So one of the things is to learn from data you can't directly see. So what does this mean? Well, what if we have a sensitive data set and we want to be able to extract macro insights or understandings from it, but actually there's limitations of us being able to see record level information. And an example of that, Ricardo introduced last week around, for example, refugee data. So it's very important that governments can understand, you know, where refugees are coming from, their needs, et cetera, in order to look after and protect some of the most vulnerable people in the world. While at the same time, the reason that they may be leaving a particular area might be because of risks from that area. So keeping their identities and their individual characteristics private is of utmost responsibility. And you can extrapolate this to, you know, a lot of the NSOs, etc., national statistics organizations, who have potentially sensitive information about the general public, and yet at the same time need to be able to extract useful information to make informed decision making via governmental leaders and politicians, etc., for the country. So we're trying to, in some settings, we're trying to learn from data we can't directly see. Sometimes we're thinking about how do we combine data from multiple data sources. So you can imagine, for example, the healthcare arm of a government trying to combine information with a census bureau or something like that to look at socioeconomic drivers towards perhaps a disease outbreak or something of that nature. But potentially joining them together makes an even more sensitive data set than they would otherwise have. So can we use these technologies to be able to combine data sets, which otherwise maybe you would not have been able to do? And third, I mean, there's a longer list we could obviously go through, but it's to share insights with the confidence that privacy is guaranteed. So I think Nisha gave some interesting examples last week where people thought they had, you know, kind of macro insights, or that they have anonymized data sets before sharing them. But unfortunately, they hadn't actually done this according to kind of a strict definition of privacy. And so reverse engineering of the original data was indeed possible, and they didn't actually protect any of the information that they really set out to do so. So this is the kind of general concept, like context of privacy enhancing technologies. And last week we covered the two kind of pillars of that, one being input privacy and the other being output privacy. We're going to see this to some degree in action through the competition. So the scenario we have in the competition is that there is a data source. So we're not going to tell you the actual data set until the competition itself. So people can't be trying to scrape the internet to try to, get side information that might be useful or anything. So the data sources are kept confidential, and you could imagine this being one data source or perhaps multiple data sources, which bringing them together is actually quite a sensitive task. So we want to have kind of strict guarantees about how that data is being processed. And the competition infrastructure really is a set of secure enclaves. We're going to go into a bit more detail about what these are. I know we touched upon it last week, but we have some people who very much work on them here today. So we're going to run secure enclaves, which are essentially like trusted execution environments, that will guarantee to the data providers that the data is only being used for its intended purpose and exactly the source code that's running the competition APIs. Layered on top of that, kind of within the enclave, we have an MPC, so multi-party computation framework that leverages enclave, that allows both the data sources to be pulled into the enclaves, but also allows for you, the data scientists in the competition, to connect to the enclaves, to authorize you and authenticate you that you are, let's say Alice from team A, who's interacting with the sensitive data and tracking your budgets, etc. And on top of that, we have the differential privacy libraries. And we've got some of the kind of most popular libraries available, including OpenDP, SmartNoise, and Diffprivlib, that are running inside of the enclaves. And so while you don't get direct access to the data source itself, or at least the complete data source itself, you can interact easily with these trusted execution environments that will keep the data sources kept safe while allowing you to process your queries and tracking your budgets, which we'll move on to in a second, from any or all of the libraries which you decide to use. And we've got this set up so you can really easily kind of get involved or send back and forth requests and use these frameworks by starter code that we've written in essentially Jupyter notebooks. And those who have a Google account, like I think you have a Gmail or anything that would work, like Google Drive or anything, you can use Google Colab, and that might just make your life even easier because then you don't have to install any dependencies or anything on your own machine. And we have buttons like literally within a GitHub that you can click, and it will open up a Google Colab session for you, which you can interact in the competition with, hassle-free essentially. And of course, it's a competition. So not only are you trying to learn and understand from these sensitive data sources, but you're also trying to make predictions based on data that you haven't directly seen. And predictions is kind of the name of the game, and your accuracy in terms of your predictions, less a loss function that we'll cover, essentially saying how much privacy did you have to give away in order to learn these insights, will lead you to a score and will put you on a leaderboard. And so throughout the competition, people can move up and down the leaderboards. You can experiment. Even if you do something really silly, at some point, it's okay. Only your top score of all time will actually be on the leaderboard. And so hopefully it's a fun way to kind of gamify the privacy enhancing technology kind of landscape. Hopefully these sessions are educational and informative and to some degree enjoyable. And you feel like you've gotten something out of it, but at the same time, you can kind of use your newfound knowledge in a competitive, interesting environment, which is the competition. So as I said, the data sources we touched upon last week with our representative from UNHCR. This week, we're going to mostly look at both the enclaves and what's running inside of the enclaves, because this is ultimately, essentially the levers which you get to pull to move yourself forward in terms of the competition itself. And of course, the second part of that is the participant interface. So the Jupyter notebooks or the Google Colabs, which you can run and you can create synthetic data, for example, pull it down onto your local machine and then try to analyze that to learn the relationships between inputs and outputs, for example. They'll be made fully available later this week, but we'll touch upon it throughout the talks. One thing we put a bit of effort into was to actually make it such that if you use any of the frameworks, OpenDP, SmartNoise SQL, SmartNoise synthetic data, and Diffprivlib, you can use them locally, and essentially you just pass through either the exact object that you've used locally or the parameters that you've used locally into just a client function call, and it will just execute it remotely for you and pass you back the results. So you don't really have to get bogged down with the details of making API calls, etc. That's kind of handled for you, and you can really focus on the data science part and understanding, the kind of privacy budgets, etc. that are going to rank you on the leaderboard. So before I continue, I just wanted to say we have a number of speakers today. So we'll be introducing them shortly. From AWS, Oblivious, where I'm from, OpenDP, SmartNoise, and Diffprivlib. Most of the speakers today are the people whose blood, sweat, and tears have gone into actually building these things. So they've written a significant portion, if not a lot, of the frameworks themselves. So I'm sure that they would definitely appreciate people getting involved. That almost everything is open source or available through GitHubs, and I think there is kind of a real ethos of open source in the privacy enhancing technologies community. So sure, you can start a repo, but actually even more interesting, try them out. If you find an issue, post the issue, contribute perhaps to different repositories, etc. And I'm sure everyone would really appreciate that. So that's just a small call to arms for the future. So before we start into the nuts and bolts of each framework, I just wanted to quickly and really at least attempt to be intuitive in terms of recapping on differential privacy, just because there's two little parts of this which are going to come up through each of the differential privacy frameworks, and it contributes to your score in the competition. So I just want to make sure everyone's kind of crystal clear on that right at the beginning. So I think the definition of differential privacy is that a randomized algorithm M with domain in the natural of X, etc., is epsilon differentially private if all S the outputs in the range of possible outputs from the queries for all X and Y. So this is going to be a real data set, and Y is going to be a data set where there's either a modification of one entity's values or the removal of one entity within that data set. There's a restriction on it, is equal to this equation. So it looks quite confusing at first, but as you start to dissect it, it can actually start to become a little bit intuitive. So what are the kind of parts going on to this? I know we sent some material on the Discord page, but I thought just kind of walking through it kind of would make life a little bit easier. So you can imagine we had some data set X, and let's say we have a friend, Steve, and Steve is in the data set X. And we're trying to guess, from making queries of the data set, whether or not Steve is in fact in the data set or he has been removed from the data set. And so we can make queries, or we could train a machine learning model on it, or we could do anything to this data set, let's say, within some space of possible things we could do. And our job is to guess whether or not Steve is there, yes or no. And so this, potentially ugly looking equation, if you don't love looking at equations, is basically saying that the probability that Steve is in the data set is going to be less than or equal to an exponential of epsilon times the probability that Steve is not in the data set plus delta. Okay, still, that might take a little second to try to digest. However, intuitively, there's two parameters. There's epsilon and there's delta. And these two parameters are going to be tracked. So every interaction that you have during the competition where you ask for synthetic data or an SQL query or training of a machine learning model or, et cetera, the epsilon and the deltas will be tracked and they can be added together. So at any point in the competition, if you asked 3 questions with epsilon 0, 1, and 2, and delta 0, 1, and 2, they can be summed together and that will be tracked. So when you make a submission, we'll know your accuracy on that submission, the epsilons that you've used so far, and the deltas used so far. But again, this might still seem a little bit like out of reach. So, there's approximately, because we removed delta here because we're assuming delta is small, but just to kind of give a sense for what these things are, we can think of the epsilon as kind of like your guessing probability, or like your guessing odds of whether or not Steve was in the data set or not. But it's like log likelihood, or log probabilities. So if epsilon is 0, there is absolutely 0 chance you're going to be able to tell if Steve was in those data sets or not. And if epsilon was infinity, you 100% know that Steve was either in that data set or not. So you can think of this as like a sliding scale of like how certain you are of whether or not Steve was in the data set. And the goal with differential privacy, differential privacy in itself just kind of tracks how certain you would be or not. But the goal of any kind of system that's trying to enforce privacy using differential privacy will try to keep that epsilon low so that it's very hard for you to guess whether or not Steve was indeed in that data set or not. It's kind of like the odds of you working out whether or not Steve was there or not. I say this is intentionally hand wavy, but I just want to make sure that people, when they're thinking of the epsilons that they're tracking, they kind of have a bit of a gut feeling of what this actually means in a tangible sense. The second part of it is the delta that's hanging off at the end. And you can think of delta kind of like the probability that more information than was intended has been leaked through the process. So the guideline is that delta should always be much smaller than 1 over the size of the data set, because otherwise you could easily be giving away information of only a small number of people in your data set. But nevertheless, you are still giving away information about people. And I'm pretty sure those, even if they're few people, would not be happy. So if you had a data set of like, let's say 10 million people or 100 million people in a census, and you actually disclosed the actual records of even 100 people in your country, like their salary, religious beliefs, where they lived, etc., there would be absolute outrage. I think everyone would agree. And so that would be a big issue. And so you want to make sure that your delta is much smaller so that the probability that you leaked any information is approximately 0, essentially. And so the structure of this competition is kind of like any normal data science competition. There's train X, train Y, test X, and test Y. You're given the train X's and the test X's. That's some information which you already have in your computer that you can explore, etc. And there's some information that's seen as private that's kept within the enclaves. And so you can try to learn about the relationship of your train X to train Y to try to predict, for example, the Y's from the X's, based on the client queries. So using the frameworks that we're going to discuss today to try to understand how X creates a particular Y. But every time you kind of learn a bit of information, it costs you some epsilon and some delta that we've just described. And then the goal is you can make submissions. You're limited the number of submissions you can make per hour, etc. But you can make submissions based on the test X to guess what test Y was. And so your accuracy of what test Y is minus a function of how much privacy budget you used throughout that process to learn the relationship between X's and Y's is your score. And that's how you're going to be basically ranked on the leaderboard. So just the last kind of notes, the score is going to be equal to accuracy minus epsilon divided by constant minus 1 minus, we'll give you this function in Python so you can calculate it. And you can obviously also call from the client to get your score at any point and how it's broken up, etc. But the idea is for every extra epsilon that you require, your accuracy is going to lose kind of 1%. So if you use epsilon of 10, you're dropping that accuracy or kind of score 10% from the true accuracy that you got. And the second part that's involved is basically a drop-off function. So provided you are much smaller than, usually about 2 orders of magnitude smaller than 1 over the data set size, which we'll give you in the competition, you know that it will have almost 0 effect on your actual score, like tiny fractions of a percentage. But if you have a delta that's quite large, your score will be totally wiped. And we have basically what this looks like as a function. So provided you're an order or 2 orders of magnitude smaller than 1 over the data set size in terms of the delta that you've spent, it will have almost 0 effect on your score. But if you are close to or greater than 1 over the data set size, your score is going to be kind of completely diminished. So you kind of really have to keep good track of that delta, but the epsilon decreases linearly. Great. So on that note, we're going to pass it over, and we're going to first talk about the enclave structure so you can understand about the input privacy, and then we'll go through each of the differentially private frameworks and libraries. Okay, so next up is Arvind. Arvind is on the kind of core AWS Nitro team. He's been incredibly helpful for us because we use AWS Nitro a lot since day one, really. And yeah, he'll give us an overview of AWS Nitro, which is AWS's enclave offering. Of course, all of the clouds have different enclave offerings today, but hopefully he can give you a synopsis of at least one of the kind of major cloud providers. So with that, I'll stop sharing my screen and I'll hand over to you, Arvind.
Thank you, Jack, and hello, everybody. Jack, first of all, thank you for the opportunity to speak here. And everybody else, good luck with the competition. The idea of my presentation is to just give you an overview of the technology that will be powering the computing that you're going to be doing as part of the competition. Obviously, as Jack mentioned, majority of what you're doing from the data processing perspective is predicated on enclaves. So the goal of the session is to tell you a little bit about AWS perspective on confidential computing and what enclaves bring to the table. Before I begin, can Jack or Clarence, somebody confirm if you can still hear me okay?
Your audio's is loud and clear, and we can see your slides with notes though. Yeah, perfect. Great.
I swapped it now, and you should see the slideshow.
Just the slides now. Perfect.
All right, perfect. All right. So thank you for the introduction, Jack, and for those of you who didn't catch that, I'm Arvind. I'm responsible for confidential computing at AWS. Today, I will be talking to you about the AWS perspective on confidential computing, and then I'll introduce the AWS Nitro system, Nitro Enclaves, and Nitro TPM, some of the confidential computing capabilities that we bring to bear today, and a little bit more about what's possible. I'll also deep dive into AWS Nitro Enclaves, touch a little bit on its key features and benefits, and leave you with some resources to work with later if you want to learn more about Enclaves itself. I'll begin by first introducing our perspective on confidential computing. At AWS, we define confidential computing as the use of specialized hardware and associated firmware to protect customer code and sensitive data during processing from any unauthorized access. The key to remember here is all of this about confidential computing is about protecting data during processing while the data is in use. The mechanisms to protect data while it's at rest and in transit have existed for a while and are pretty mature processes. Right now, what we're dealing with is after the data has been brought to the CPU and decrypted and is about to get processed as plain text. How do you protect that? And who do you protect it from? In talking to our customers, we have identified 2 distinct security and privacy dimensions from which code and data in use needs to be protected. Of this, dimension 1 is where customers are most concerned about protecting the data from the operators on the cloud provider side. In our case, that will be AWS. And dimension 2 is where customers are more concerned about protecting highly sensitive data and code from even admin level users or users who could pose as admin level users on their side. So to put it very simply, dimension 1 is about protecting your code and data from us, and dimension 2 is about protecting your code and data from yourself. And confidential computing is protecting customer code and data while it's in use, regardless of which dimension is in. How we go about achieving the protections from dimension 1 and 2 is what we will talk about next. If you have any questions along the way, please feel free to drop it on the chat. I cannot see your chat right now, but once I'm done presenting in a few minutes, I'll go back and take a look at the chat and start putting answers down for your questions. So here's an overview of some of the confidential computing capabilities that we have. It all begins with our AWS Nitro system. All of the Nitro-based instances that you see today from AWS are built on the Nitro system. The Nitro system is the foundation of the virtualization of all modern EC2 instances and addresses the dimension 1 we talked about in confidential computing. What that really means is if you were using a Nitro-based instance today to run any of your compute needs, you are by default protected from any AWS operator from being able to access your data or code. Nobody from AWS can access your code and data, and you get that protection by default. There are no mechanisms, no APIs, nothing in place. And the AWS Nitro system already isolates the host away from any operator, even from the infrastructure stack itself. Then comes AWS Nitro Enclaves, which provides a hardened and highly isolated compute environment to further protect your data and code. And this is what addresses dimension 2. And I will go over how this addresses dimension 2 and how it ensures that nobody has access to any of the data or the code that's running inside the enclave. And then lastly, the Nitro TPM, which allows for cryptographic attestation of the health and integrity of the Nitro instances itself via the TPM 2.0 standard. So if you have workloads today that are running on-prem and rely on TPM 2.0 and you're looking to move to the cloud, this is a good solution that will enable that kind of workload. So what is Nitro Enclaves? Before I introduce Nitro Enclaves, let's first take a look at what a standard EC2 instance looks like. So this is a good representation of what a standard EC2 instance could look like. And inside the instance, you have multiple users who could have access to the instance. You could potentially have third-party libraries that are running in there. You could have your own applications and an OS that's running in your instance, which means a lot of these potentially has access to the data that is going to be processed in the instance. So even if you had encrypted data that was stored and that was moved in an encrypted fashion into your instance, once it hits your instance, if you want to process it, you're going to have to decrypt that data. Once you decrypt that data, plain text data is going to get revealed to all the other entities we talked about outside that yellow box inside this instance. So how do you protect that? Because once that plain text data is revealed, then at least at the minimum, an admin level user could potentially have access to this. And that's what you're trying to lock down. And that's where Nitro Enclaves comes in. Nitro Enclaves provides additional isolation to protect this data in use. The way this works is you have your standard EC2 instance from which you could carve out CPU and memory resources to spin up an enclave. The enclave is now only connected to the parent EC2 instance through a secure local channel. There is no other connection that goes into or outside the enclave. Nobody can reach into an enclave, and only the enclave can make calls from here on once you spin up the enclave. Now, if you move your encrypted data inside the enclave, then you could securely decrypt it and reveal plain text data into the enclave only, which means if you were running an application to process data in the enclave, that application can securely process plain text data while retaining all of that inside the enclave. The parent instance never gets to look at the enclave, and no other external entity can look inside the enclave either. So this allows for plain text data to be securely processed. This allows for multiple data sets that can be brought inside the enclave as encrypted data sets and then decrypted. So whatever applies for a single data set here also applies for multiple data sets. That's why this is a solution that's very suited, if you will, natively for multiple data set processing as well, which I'm expecting is machine. It has its own lightweight Linux OS in there and an independent kernel. More importantly, the enclave has its own encryption keys. It always retains its private key, and it could send out the public key with anything, with the data, with the key, with other keys that it's fetching and whatnot, to wrap it and send it out. And the enclave is the only one that can decrypt anything that's been encrypted with its public key. The enclave looks like a container because it's ephemeral. We also use the Docker process to build the enclave image file, but it is not a container. The enclave does not have any persistent storage associated with it. There is no administrator, root user, operator access from a parent EC2 instance into the enclave. And this is what's most important, because all along we talked about this dimension 1 and 2. How do we really protect this from dimension 2 is where we are isolating the enclave and making sure that nobody has access into the enclave. So if you're a root user, you could not access that shit to the enclave if you wanted to. There's no way to see what's going on inside the enclave after you've dropped your data in there for a pre-validated application to run in the enclave. The enclave also has no external networking either. There's communication only over a secure VSOC channel to the parent instance only. So once you've revealed plain text data, it's incumbent on you to make sure that you're not passing plain text data from the enclave into the parent instance. Everything stays in the enclave while it's getting processed. Once it's processed, you could re-encrypt it back again and send it out. That's the whole idea here. The enclave also has a unique ability. It can prove its identity to any external entity. When we talked about the Nitro-based instances, I glossed over it a little bit, but one of the key components of the Nitro-based Nitro system itself, which is what the Nitro instances are built on, is the Nitro hypervisor. The Nitro hypervisor is a lightweight hypervisor that actually takes care of some of the ring-fencing of the instances that are carved out from the host. The Nitro hypervisor signs an attestation document per instance, and it can also sign the attestation document for the enclave. And what this allows the enclave to do is provide proof of its identity. The attestation document contains measurements like hash of the enclave image, the application that's running inside the enclave. So if you have a software that's sitting in the enclave, you can have a hash for that. So if anything happened to the software changed, then the hash is not going to match what's going to be calculated at runtime. The measurements also include the parent instance ID, the AWS IAM roles, and can even do a user-defined info like a nonce to avoid repeat attacks. And the enclave, of course, has its own public key, which it sends out. We have integrated Nitro enclaves with a service, with an AWS service called AWS KMS, which is our key management service. This is an example for you to know what an enclave can attest to. You don't have to use AWS KMS. You're free to use any key management service you want. The only difference is we've written the APIs to make the calls and to use the attestation document. So I will give you a very quick overview on how that works. The enclave produces its attestation document, which is being signed by the Nitro hypervisor, and shows it to a service like a key management service and says, hey, here is who I am, here is proof for who I am, send me the keys. Key management service is now going to receive the attestation document and compare it against a preset key policy. It's going to check these measurements to see if the enclave really is who it says it is, and if the application that's running inside the enclave is what is expected to run in there. Once it validates that, then it releases the key to the enclave, which allows the enclave to decrypt the sensitive data that you've now dropped inside the enclave. This is an example of how attestation works and an example of a service that we have integrated with. Like I said, you're free to use any service. You're just going to have to write the APIs to make sure the attestation process can be fulfilled. Lastly, I just want to touch on the key features and benefits. Enclave, as I said, provides additional isolation on top of what EC2 instances already provide for you. There's no persistent storage, no interactive access, no external networking, which really allows for total isolation of the enclave from any unauthorized access. and it only communicates to the parent instance using the secure local channel. The enclave is also very flexible. Number one, it's processor agnostic. So you could potentially use Intel, AMD, or even our Graviton processors from our fleet and not be tied to any CPU vendor when you use the Nitro Enclave technology. The enclave also allows you to carve out varying combinations of CPU and memory from your instance. So you can really use very small instances if you like, or very large instances if you want to create large enclaves. There's a high degree of flexibility in what you want to do with the enclave itself. So you could choose an instance which is large, but you really only want a small enclave because the sensitive data processing is super small. You could potentially do that as well. And lastly, the enclave provides cryptographic attestation, which allows it to prove its identity and authorize the code that's running inside the enclave. We have integrated with a couple of services to provide seamless execution for you. But again, you're not tied to any of the services. You could potentially write the APIs yourself for any service that you want the enclave to attach itself to and to interact. And lastly, there's no additional cost to using Nitro Enclave. So if you're running an EC2 instance, it's as simple as checking a box from the console to say, I want an enclave to spin up, and here are the resources I want to dedicate to the enclave, and you have it. I'll stop with that and leave you with some resources to go and check on later if you're interested in learning more about enclaves. Number one is go.aws/enclaves to learn about enclaves. And lastly, for those of you who are working hands-on in this thing, we have a free workshop. It takes about 2 hours to do. It helps you spin up an enclave, drop an application in there, and tells you how to work with enclaves in general. I'll stop with that and pass it over back to Jack. Thank you for the time and good luck with the competition, everybody.
Thanks a million, Arvind. Great, so that's fantastic. I would say, obviously, enclaves are available on all of the major cloud providers. We've used AWS a lot, and it's incredibly flexible. So, I mean, you can a lot of flexibility in terms of the sizes that you can spin up, etc. So you can create very large enclaves, which was of priority to us at a certain point. So just to recap, at least, if you just want to, as a takeaway from enclaves, or how I think of them generally, is that they're transparent at build time. So when you boot up an image, when you boot up a program to run, it's hashed, and that's what's going to be guaranteed by the attestation. So the source code that you spin up when it's first spun up, it's going to be guaranteed. So it's so you know exactly what's running inside, but it's opaque at runtime. So when you send in sensitive data, there's not going to be someone who can just SSH in and see the data as it's being processed, or your data is not going to end up in a sensitive in a log file, etc. And from our perspective, especially in the context of MPC and in the competition, when you connect to an enclave and you send sensitive data, you can have guarantees that that data is not going to be sent outside of the enclave or used for purposes outside of its intended kind of function. And that mechanism, which is what kind of guarantees what's running inside, it's called attestation. And it's basically like a digital certificate given to you by the underlying infrastructure provider. So how does this actually fit into a competition, right? Because you have multiple people connecting in, and then you have obviously multiple data sets being pulled in as well. So what we do at Oblivious is essentially let you write any like fast API server or any NPM JavaScript server or Java or whatever you want. If you can write a server or a microservice, you can just build it. And instead of running it in a Docker container, we essentially add an extra layer on before it gets run as a secure enclave. And what that does is it takes your server, your code, and it runs it as the user-defined process, but it actually runs it in the context of a service manager. So one thing is like spinning up and down Docker containers is very, very quick, but enclaves is a little bit slower because you're actually dealing with virtual machines, etc. So a service manager can make sure that if anything was to crash, it could be spun up very quickly without having to tear down the infrastructure. There's an access control manager, and this is what, when you connect into the enclaves to basically say, hey, create some synthetic data or run this SQL query, etc., it's going to know who you are, what role you have, what paths you're allowed to connect to, etc. And that's basically configured at the point when you're describing basically how the enclave should work. And that's access control inbound, but also outbound. So it is possible in certain circumstances that you need to make an outbound call, but we essentially allow you to allow list this based on FQDNs, so fully qualified domain names. So if you need to speak to example.com, you can create a HTTPS connection from inside the enclave, the way you would call, from a normal computer. And if you're not on that predefined list of approved FQDNs, then your request will just be blocked. But if it is on that list, you'll create a HTTPS session from inside of the enclave. So even the host, whose cloud account it is, can't see the data that's being transferred to or from that FQDN. And all of the business around virtual sockets typically aren't super convenient for certain applications, especially if you run like REST APIs, etc. And so we obfuscate the vSocket proxy by proxies, etc. So if you can just build a normal server that runs as a microservice or a server, you can basically give a little bit of metadata to say how users can interact with it. And the whole thing gets spun up as a multi-party computation secure enclave. When you're connecting in for the competition, what's happening under the hood, there's a proxy there for you. But initially you do a client hello and you say, hey, I am, let's say Steve. So I am Steve and here's my public key. And inside the enclave itself, it generates a symmetric key. So even the infrastructure provider can't see that key itself. And it encrypts that symmetric key with the public key that you've just given it. And it embeds that into the attestation document that's going to be signed by the underlying infrastructure. So anyone who sees that can't actually work out what that symmetric key is unless they had your private key. So that gets sent back to you. On your side, the proxy validates the cert issuer is indeed AWS. It verifies the signatures that you're connecting to the enclave that you think you're connecting to. It verifies those PCR codes, which are the hashes that are telling you that it's doing exactly the source code, etc., or the image that you expect to be running in there. And it extracts that symmetric key. And now all of the traffic that you send back and forth to the API that's running inside of the enclave is encrypted with that symmetric key. And that gives you a guarantee that even if you're connecting to someone else's AWS account, they can't see the data itself that you're sending to that enclave. And so this is really important to make enclaves useful for multi-party computation. So multiple people can send data or queries to a trusted environment where they don't have to trust one another, but they're actually trusting the underlying physical infrastructure of that particular cloud. That's exactly what's going to be done in the competitions. You can do it directly from your Google Colabs. I can show you what that looks like. It's literally a two-liner from Google Colabs. We also will give instructions if you're running it from Jupyter Notebooks on any of the other Linux variants, Mac and Windows. But essentially, you just pull down, in the case of Google Colab, Debian image, and you just install it onto the machine. And once it's installed, you can actually run an OBLV connect, which is that proxy connection. And there's three components to it, but it's fairly straightforward. The first three are these big long strings, and they're the hashes that dictate that you're connecting to the thing that you expect to be connecting to. And we'll give you those hashes as we plan to open source everything. So as well as all the code that's running inside of the enclaves. So you know what you're connecting to. Each participant, not each team, but each participant within the team as well, will have their own public-private key pair. So you just upload that into Google Colab or have it locally in your Jupyter Notebook. And just specify where they are. And finally, there'll be a URL, which is where the enclave lives. So when you speak to that, it goes through, like typical firewalls and load balancers, etc. So all of the classical securities in there too. But you need to know obviously where you're sending it to. So the URL dictates that. And the last thing is this L port, which is your local port. So in this case, it's 3030. So whenever I send a request to, let's say, localhost port 3030, that will get encrypted on the fly. You don't need to think about it. Sent all the way into the enclave with the guarantees that you're connecting to the right thing, that no one's going to see your data from your computer through to it being inside of the enclave. And it will get any responses decrypted on the fly and pass it back to you as plain text. So it abstracts away a lot of the low-level kind of cryptography that you would have to do. and it packages it so you can just use MPC out of the box. Once you've got it set up, life is very simple. So the frameworks that you're going to see, either the objects themselves, we'll give all examples of this later in the week so you can play around with it yourself. But you can, you just call the client. SQL would be the SmartNoise SQL framework, which you'll see a little bit later on. So you just pull in the client, you say which port, sorry, 3031 in this case, that the proxy is running on. And all you have to do is say, hey, run this SQL query for me. Use this much epsilon and this much delta, and give me the result. And the result is passed back to you in this case in a data frame, which you can then use to explore, to understand. If you're creating synthetic data, you can then do some analysis on it, et cetera, et cetera. But it should all be fairly straightforward. And of course, a lot of this seems quite complex when it's in the abstract. Okay, there's a typo on that slide, but nevertheless, it can seem quite abstract in the kind of, when it's out there, but we actually give full implementations with starter code for everything. So you don't have to guess, the tools or the interfaces or anything. They're already there for you. You can change your epsilons, you can change what queries you're making, you can change what synthetic models you want to use, you can change anything you want, essentially, how you want to interact with that data, but it's all end to end kind of there for you in terms of the steps. So if you learn about the libraries we're about to speak about today, then you're going to be totally set for the competition itself, because the interface is basically you just passing them to a function that looks after the rest for you. Great. So with that, I will pass it now over to Michael Schomut, who's from Harvard and OpenDP team. He's a core developer from OpenDP, and he'll introduce OpenDP, which is, we've gone from the physical infrastructure. OpenDP, I'd say, is the most granular of the frameworks, and then we'll go less and less granular. So we'll go into SQL queries and synthetic data, and then Diffprivlib that will actually allow you to run like a machine learning model, like a random forest or PCA or something on the data as well. So with that, over to you, Michael.
Great. Let me get my monitor shared. All right. So everyone hear me? All right. So
Yes,
my name is Michael Schomut. I'm part of the OpenDP community, and I'm a developer on the OpenDP library. Given an introduction to the library today. The OpenDP library is a modular collection of statistical algorithms for releasing differentially private statistics, and it's implemented in Rust and has bindings from Python, which you'll be using in this hackathon. You can find the repository here under software. And the install is pretty straightforward, just pip install. We actually don't have any dependencies, so that's really lean. I'm gonna switch over to the user guide. So I'm gonna show you the latest docs today because we're anticipating a release tomorrow. This has more information on getting started, but I'm gonna skip forward into the programming framework. The library is built based on a conceptual model described in this paper, a programming framework for OpenDP. The biggest thing I want to draw your attention to is what a measurement is. A measurement is it's a randomized mapping from a data set to some DP release. And basically, measurements encompass any function for which you can pass data in and get DP releases out. It's kind of like a mechanism. It's essentially a wrapper for a mechanism that if you have any prior knowledge of DP, you might recognize that word. But the measurement has a specific meaning for OpenDP, mainly that it consists of 6 pieces. an input domain that describes the set of possible inputs for the function that you pass your data into, an output domain describing a set of possible outputs, the function itself that computes some DP algorithm on your data. Whenever you have a measurement in hand, you can call the function with this shorthand or measurement data. And then there's also an input metric which describes how distances are measured on the input. So depending on how you constructed your measurement and what your function represents, the input metric can correspond to the number of contributions an individual may make to the data set or the sensitivity of a query. So like in the context of this hackathon, we'd want the input metric to correspond to some kind of count of the number of contributions that an individual can make to the data set. And we also have an output measure, which corresponds to your definition of privacy, like pure DP or epox DP or zero concentrated DP. And then finally, a privacy map. And this is also a function. You pass in the number of an upper bound on the number of contributions an individual can make, and it returns epsilon, or a privacy parameter that captures how private the computation is. So these pieces together allow us to give an encapsulated, self-contained privacy guarantee and prove the correctness of each of the measurements that you can construct with the library. There's also a transformation, and it's very similar in concept to a measurement, but in this case, it's not a function from a data set to a DP release. It's a function from a data set to a data set, and it's useful as a building block to build more complicated measurements. So the transformations reason about the stability of a function. So it's you might say like a transformation that represents a bounded sum. Reasons about the stability of a transformation in terms of the sensitivity. And once you chain it with a measurement, like base Laplace, you have a end-to-end computation chain that relates distances in terms of contributions to distances in terms of how private the computation is. At this point, I'm going to switch over to a notebook, kind of going down into the APIs of the library. I'm going to start out by opting into contrib. So we're working towards writing proofs and embedding every constructor in the library, but not everything has been formally proven. We're confident in the correctness of our code, but we're also accompanying it with LaTeX proofs, and so anything that hasn't reached that point of stability is marked as contrib, and in practice, it's best to enable this to start using the library. So what I'm going to do here is pull down a constructor function. Most of the library interface consists of constructor functions. These are functions you can call with some relatively straightforward parameters that will return a measurement or a transformation. So in this case, I invoke this constructor. I'm constructing a measurement for which it adds Laplace noise with scale of 2. And you can pass an aggregated value in. Let's say this is a sum, and it'll noise it and return the noisy DP release. If we want to work out what the epsilon for this measurement is, you can use the map, as mentioned before. There's a privacy map on measurements. You pass in the sensitivity of the query. That's the largest amount that the query can change if one individual is changed. And it'll spit out an epsilon. The Same can be said for transformations. So you can pull down a constructor function from the transformations module, and you can call it with, in this case, some bounds to construct a bounded sum transformation. And here, when we invoke the function, we pass in our data set, and it returns the exact bounded sum. And again, similarly as before, we have a map function that takes, in this case, the maximum number of contributions an individual can make, and it tells you what the sensitivity of the function is. And you'll notice here that since our bounds were 0 and 1, you might say, well, if an individual can contribute at most one record, then the largest amount that the sum can change is just 1. It's a little bit larger here because it correctly accounts for things like floating point issues, so that the resulting guarantee is correct, even under finite data types. And so moving on, I can use this right shift operator to chain the transformation we just constructed with the measurement from before. So when I invoke this new measurement with my data, it gives us a noisy, differentially private sum. So it was 196 before as the actual underlying data. The noisy value is 196.7. We can also reason about the privacy guarantees of this chained computation with the map. Now, in this case, the input is the number of contributions an individual can make, and the output is epsilon. And I'll switch back over to the user guide. So mainly what I've talked about so far is a programming framework. This notebook, A Framework to Understand DP, gives some more background and goes into more detail on what metrics we use and how we represent differential privacy in the framework. But if you're ready to hop into code, this is a listing of the constructors available in the library. It's broken into 3 categories. We've got transformations, measurements, and combinators. Combinators are also constructors that return transformations, but they're a little bit higher level because they're also constructors that return transformations or measurements, but they are a bit higher level in that they operate over other transformations and measurements, like chaining or composition when you want to release multiple DP statistics at once, or when you want to cast the privacy definition. You have a computation that that has a guarantee in terms of maybe 0 concentrated DP, and you want to figure out what the corresponding guarantee in terms of approximate DP is. So the combinators are useful whenever you want to do some higher level operations on other measurements and transformations. So I'm going to move on to utilities. There's 3 broad sections here under utilities: typing accuracy and parameter search. They'll go over how you configure things like the Laplace that I've already mentioned to work on vector value data, or how to configure the underlying data types. And then we have the accuracy module for releasing confidence intervals, and parameter searches for when you want to solve for other parameters in your computation chain beside from just the epsilon output. I'm going to put these all together, these utilities and the constructors, in a kind of an overarching example. Let's say of a CSV dataset consisting of student exam scores. Let's say we have a privacy budget of 1 epsilon, and we want to compute an accuracy estimate of the DP result with 95% confidence. So let's say that there's some public knowledge that there's only 3 exams, so that means the number of contributions is bounded above by 3. And I'm going to grab a bunch of constructors from the transformations section to build a transformation that takes a CSV and emits aggregate mean. What it's going to do is parse the data, select a column out, do some casting, imputation, clamping. This one establishes a bound on the dataset size, which is useful for bounding the sensitivity of the mean. And so what I've got here is a transformation. It's not DP yet. Next, I'm gonna calibrate a measurement that gives us the right amount of noise, so that the resulting measurement is 1 epsilon DP. So I use this utility from the module to grab a scale parameter that would work for us, and then construct the measurement out of that. So then if I invoke the measurement with some mock-sensitive data set, it should result in a value of somewhere around 95. It'll be noisy. And the epsilon expenditure of invoking this function is 1 epsilon. Then I can also use the accuracy module to convert our scale parameter to an alpha, a confidence alpha significant. It has like a 1 minus alpha 100% probability of returning something outside the interval. Together, this tells us that for the given choice of epsilon in the discovered noise scale 2, the DP estimate differs from the true value by no more than this quantity at our statistical significance level. So it's useful for building not just differentially private outputs, but accuracy guarantees on those outputs as well. Last thing I want to mention is we have this really useful API documentation. If you go down into the API documentation for, say, make-based Laplace, which we had called earlier, it gives a lot of useful information about the kind of parameters you can pass to configure it to be more general. So at this point, I've kind of given what I want to give. I thank you for your time. I would love to chat more with anyone who's interested on Slack or through our discussion board on GitHub. So keep in touch. Thank you.
Awesome. Thanks so much, Michael. And just to clarify as well, so these like pipelines which are being built up, that so you have the data set, obviously that bit's provided for you, but you have a mock data set in the Jupyter notebooks in the starter code, and then you can make the transformations and the measurements, etc. And you literally take the object which you've created and you just pass it to the client, and that will be executed for you, and you'll get back the result. So we do check to make sure that you're passing something that's differentially private. Yeah, if you just say, hey, get me all of these results, that will not be blocked. But if you follow along the tutorials that Michael's shared on the there's actually, I think in the OpenDP GitHub, there's a number of like sample Jupyter notebooks as well that people can follow along as well. That will just get you familiar with just making transformations. You know, agnostic of the competition, but it's very relevant to, you know, you can make the same transformations in the competition, for example. So thanks a million, Michael. Great. So I think OpenDP is like one of the kind of core libraries, because it's you can really make like low level like measurement, like transformations and then measurements of specific data. But then there's also frameworks that are built kind of at slightly higher level of abstraction on top of them. One of which is the SmartNoise project. And we're very lucky to have Joshua Allen with us. He's, I believe it's a senior data scientist with Microsoft who focuses on building SmartNoise, I'd say in particular, but privacy enhancing technologies. But if you go on GitHub, he wouldn't say this himself, but I think he's written 85, 90%, 95% of the SmartNoise framework. So if you have any questions on SmartNoise SQL, which I'll introduce, and SmartNoise synthetic data, definitely ask the questions, because I think there will be no one who will know the answers better than he. So with that, I'll pass you over to Joshua. And thanks, Josh, for taking the time.
Okay, so yeah, thanks for the intro, Jack. So SmartNoise is a set of Python routines that are built on top of OpenDP and allow you to run SQL queries, differentially private SQL queries against an array of SQL backends, including against pandas data frames. And we also include some routines to generate differentially private synthetic data that looks like, you know, your source tabular data. So we'll talk a little bit more about, you know, where you would use each piece when we get into the demo. But at a high level, the guidance that we give people is that you should use OpenDP directly if you need the maximum control over your privacy budget spend. And, you know, if you want to have the maximum fine tuning of how the algorithms work and so on, then you'll use OpenDP directly. And the SQL layer is nice if you have an existing fact table, you know, an existing data set that you have existing SQL query workloads over. SmartNoise makes it fairly easy for you to just drop in differential privacy without having to change much of your existing workload or even your code. And it's also nice for kind of ad hoc exploratory sessions where you want to, you know, very quickly, without having to write code or, you know, without having to learn a lot of new syntax, you can understand some things about your data set. Then synthesizers, of course, are useful when you have really no idea what the workload is going to be and you want to share some looks like data with other partners. And one of the nice things about synthetic data is that you spend your privacy budget once during the training process. And then when you pass on that synthetic data, you can indefinitely query that synthetic data without incurring any additional privacy spend. You know, and there, as I said, there's some other caveats which, you know, hopefully we'll be able to mention here with the demo. All right, so to start this demo, we're going to read the PUMS microdata. And this is the PUMS data set that is just 1,000 rows. So this is a down sample of the California PUMS census microdata. You can see that we've got a bunch of demographic information here. And for the purposes of the demo, we're just going to look at a couple different, you know, a one-way marginal and a two-way. So at first, we can see that the number of married people is about 100 more than the number of unmarried people. And if we look at their ages, then we can see that unmarried people on average are about 7 years younger than married people, which, you know, kind of makes sense. All right, so now let's make a private SQL connection to that. So one of the key things with the SQL layer is that we wrap around any existing SQL connection. So this is if you have a Postgres connection or Spark or SQL Server, BigQuery, etc., then you just give us the connection. So that's what this from connection method is. In the case of a pandas data frame, though, we will transparently put that data into an in-memory SQLite database to allow the SQL queries to run. So that's why, if it looks weird that we're not actually using a SQL database, that's behind the scenes, we're actually doing that. So essentially, you just need to give us a connection, and you need to give us a privacy parameter. And this parameter determines how much epsilon and delta gets spent on computing each statistic. Oh, and the third thing you have to provide is this metadata file. And I'll show you this. The key reason that we have this metadata file is because we need to know the upper and lower bound of numeric columns, and we need to know which columns you want to treat as categorical. These are things that we could infer from the data, but with the SQL layer, our assumption is that the data curator or the data owner knows this sort of schema information and can provide these sort of bounds in a way that doesn't require us to spend privacy budget and is going to be more accurate. So for example, with age, here we just specify that the age is between 0 and 100. Whereas in actuality, the underlying data, the minimum age is 18 and the maximum age is 93. But of course, if we used our differential privacy bounds based on 18 and 93, that would actually leak privacy because we would leak the fact that the oldest person in the database is 93. So one of the things we could do is we could infer the approximate bounds, but those could be wildly inaccurate, depending on how much budget you have to spend. And you don't really want to spend privacy budget on inferring things that you know already. So I just mentioned that that's why we have this YAML format. It's pretty straightforward. It's heavily documented on the docs on docs.smartnoise.org there. There's some other things you can do in there. Like in Michael's demo, he showed you that you can do the maximum contributions per user. So that's another parameter you could put in here. If you have a fact table or something that allows users to appear more than once, then you can specify in here and we'll automatically do the reservoir sampling and stuff for you. So that's the idea with the metadata file. So let's just run a query. All right, and you can see here that the numbers, they're pretty close. Yeah, I mean, just one of them is off by 1. And if we run this query repeatedly, you're going to see that there's some noise added. Oops. Yeah, but with an epsilon of 1, yeah, I mean, it's changing, right? So yes, it's a noisy answer. Yeah, and then we do the same for the average ages, and you can see if we run it repeatedly, then you get a different noisy answer each time. And so the idea here is that this .execute method is the same method that you would have had on your Postgres cursor or on your SQL Server cursor or whatever. So it's essentially a pass-through. Now, one of the other things that I want to highlight, remember we mentioned that this epsilon is the amount that's used to compute each statistic. And so in this case, we have a count and we have an average. So I'm going to go here and I'm going to start over and run that query, and then we're going to check how much budget has been spent. And so you can see here that we've used epsilon of 3. The reason for that is that the count used an epsilon of 1, and then the average was composed of a count and a sum, which each used an epsilon of 1. So the total epsilon is 3. And that kind of underlines why we use this pattern where instead of giving a fixed budget ahead of time for your entire query workload, we don't know what your query workload is going to be, right? After you've spent this epsilon of 1, we don't know what other queries you're going to ask for. And so we treat it like an odometer where we just track how far you've gone in terms of spending budget, and we let you monitor that budget. So I just highlight this because there is a facility in the framework if you know a fixed workload ahead of time, if you've got 100 different queries you want to run, you can pass those into the framework without running them, estimate the total epsilon, and then then adjust your epsilon until you get the total budget spend that you want before you actually spend the budget. But just the general mode is that you're just doing an odometer. The other thing to highlight here is that if we do these same two queries in a single query, so, again, we're going to have a count and we're going to have an average. In this case, the framework can assume that you want to use the same count as part of your average. And so in that case, you're only spending an epsilon of 2.0. So that's just one of the nuances of the way the budget works that I wanted to call out. I guess, some other caveats about the SQL layer is, obviously, as with anything else related to differential privacy, as your sample sizes get bigger, the noise created by differential privacy becomes, small comparatively. The accuracy, starts to fall within sampling error. And so something like this SQL layer on large data sets can get, very high performance that's, essentially indistinguishable noise. And that was one of the reasons that we build this to run against the backend SQL engines, because if you run this against Spark or BigQuery, all of the heavy lifting gets done in that engine. So you can run this over petabytes of data. It will let BigQuery or Spark go do all the hard work, and then OpenDP will apply the differential privacy. All right, so let's go ahead and do the exact same thing, but with synthetic data. So in this case, you just create, you just import the synthesizer namespace or synthesizer class here. And so with a synthesizer, you just need to provide us with a data set. And this data set can be a list of tuples, which is just your standard output from any SQL query. So you could do like a select star from some database to get your data set. You can provide us with a NumPy array, or you can give us a pandas data frame. Now, in this case, I'm loading the same data that we were just looking at, but I'm going to drop the income and education columns. And this is just purely for demo purposes, because these are pretty high dimensional columns, and it would take about 10 minutes to train that synthesizer. So if I drop them, the dimensionality gets a little bit more reasonable. And so this is where you call synthesizer.create. Pass in an epsilon. We're going to say verbose because we want to see some diagnostics. And the thing here, I'll show you the synthesizers that we have available. Yeah, so we've got, a fair number of differentially private synthesizers available. 3 of them are based on marginal based, so you need to pass them categorical type features. Pre-process your data so that it's binned into categories. And then we've got 4 synthesizers based on neural networks. Then this hybrid synthesizer here was actually designed to work with the sort of models that you're going to see in the Diffprivlib session, where we can work in hybrid with other models to make better synthesizers. All right, so in this case, we're going to use the MWEM synthesizer, which was the first differentially private synthesizer created and is still fairly good. So we create it, we've got our synthesizer, and now we want to fit that synthesizer. You'll notice right here, I'm doing this preprocessor epsilon. What this is saying is to take a portion of the budget that we've allocated and use it to infer the approximate bounds of the data. So you remember with the SQL example, we were using metadata to say what the bounds are. But in this case, I'm just showing if we don't want to specify what the bounds are, we can infer them, and we're going to spend half an epsilon to do that. And so you'll see it gives you some information. The total number of distinct dimension combinations is about 1,700, 15 total cuboids, et cetera, et cetera. And by default, MWEM is going to run for 30 iterations until it gets a good fit. Now, these are all of these synthesizers have a bunch of hyperparameters, and those hyperparameters are documented up on the site. But in a lot of cases, you won't need the hyperparameters. Okay, and then this is where, now that we have this synth object fit to the POONS data, we can sample from it an arbitrary number of records. So we're going to sample 1,000 records to make it be the same size as what we had before. We're going to take a look at it, and sure enough, it looks like the original data. But let's see how accurate the counts are. So, this isn't quite as accurate as we had with the SQL data, but, you're still looking at, more married people than unmarried, off by 100, 150 or something. Let's look at the ages. Yeah, and so in this, with the synthetic data, the married people are older than the unmarried people, which is what you expect as well. But you can already see that the utility of this is not as high as if you just do the SQL queries directly. Now, in the SQL queries that we did directly, it should be almost equivalent accuracy as you would get by using OpenDP directly. But even with the SQL one, for some of the reasons we highlighted, you may not get as precise of epsilon budget spend as you would with getting OpenDP. And so that kind of issue gets compounded with synthetic data because the synthesizer doesn't know what your query workload is. And so the synthesizer was trying to learn a bunch of other marginals. So it was trying to learn the number of married people by race and the age of people by race. And it was trying to learn all these other things that you may never query. And it spent epsilon budget to learn those things. And so that's why some of that budget was wasted and you didn't have as much budget left to learn these other things. And then, getting back to, one of the other themes here about inferring these approximate bounds, it could be that, the bounds that were inferred ended up, being much higher than necessary, which kind of skewed the values in a certain direction. And so, of course, if you go retrain the synthesizer and run the process again, it may find different bounds and you'll end up with slightly different answers. So that's just, one of the drawbacks of synthetic data. All right, so I'll just talk quickly about one of the things that you can do, like if you know the bounds and you want to be able to more finely control what goes into the synthesizer, we provide some reversible data transforms. So these are similar to the transforms in OpenDP. These are based off of the reversible data transforms library out of MIT, out of the SDV project. And the idea with these transforms is that they can take your source data, transform it to some internal representation that's optimized for the synthesizer. And then when you sample the records, it will reverse the transform. So, a really common pattern here is that when you're using neural network-based synthesizers, you want your categories to be one-hot encoded. And you generally will want your continuous values to be scaled between -1 and 1, or maybe scaled to be a standard normal. And there's cases where, like in this PUMS data set, the income is sort of an exponential distribution. So if you log transform it and scale it between -1 and 1, then you're going to tend to get better fits when you fit the synthesizers. So this is all covered in the documentation, but this is just a set of libraries that you can use. So in this case, we're taking column by column. We're saying that we're going to have a lower 18, upper 80. We're going to bin this into 60 bins because the marginal based synthesizers need bins. And then the rest of them we're just going to bin based on their labels. And, again, what? Oh, I forgot to run this. Okay. Yeah, and then, it's the same thing, but you see our number of dimensions is a little bit different because we hard coded, every bin here rather than letting it infer things, and we can go through the whole process again. So I'm not sure if there was anything else I would cover that's relevant. Yeah, one of the things that I will mention with synthesizers, because we do make use of these, internally at Microsoft, and one of the things that we've encountered is that in some cases, for certain tasks, the synthesized data will perform better than even the non-private data. And one of those scenarios where we've seen that happen is with classification tasks. So I don't want to say that this is a rule of thumb because it's, less than 10% of the time probably that we see it. But sometimes it just is the case that if you train a classifier on differentially private synthetic data, you get better results than if you had trained it on the original data. And so, the thought is that the differential privacy itself is doing the function of regularization, and it's helping to make the data generalize better. There may be some other things going on, but it's just one of those things where if you look at these results, you would tend to conclude that synthetic data is going to give you the worst utility possible. And that's, a trade-off that you're making because you want the flexibility that synthetic data gives you. But in fact, you don't really know until you try. Sometimes the synthetic data will actually give you better utility. So something to keep in mind. Oh yeah, I guess one other thing that I'll mention, as I mentioned with the SQL data, if you have really large data sets, you can use very small epsilons, you get very good utility and so on. So in data warehousing or reporting type scenarios, it works very well with the SQL. You have a similar trade-off with the synthesizers, but the way that you take advantage of that is a little bit different because the synthesizers, if you see here, like when we run MWEM is keeping track of 1,700 dimensions in memory, and it's trying to count all these in memory. And this is pretty simple. This is a very small number of columns, but you can very rapidly get into dimensionality where there's billions of possible dimension combinations, and they just simply won't fit in RAM at all. And so there's really no way to train those. Even if you get up above, 10 million in your dimension combinations, then the fitting process is going to be very slow and so on. So the way that you scale the synthesizers, if you have a lot of data, is you'll partition the columns to make the dimensionality smaller, and you can partition the rows horizontally. So, if you have 1 million individuals and you break those into 10 partitions of 100,000 each, then you can train 10 synthesizers in parallel. You don't have to count the epsilon 10 times because these are different individuals. And then you can ensemble those synthesizers. And in our experience, those kind of ensemble approaches, when you have big data, can get extremely high utility on the synthesizer, like, kind of indistinguishable from the original data. So it's just one of those things with everything in differential privacy that more data makes things easier. And I think that's all I had to cover. So back to you, Jack.
Yeah, excellent, Josh. And one thing I would say is, so obviously SQL is quite accessible for people who even might have like less experience with some of the data science tools. You can make kind of SQL queries, but even if you are very unsure of like what to do in the competition, just creating some synthetic, maybe on we'll have like PUMs and like other data sets available. You can just download to try them out locally. But starting off by just creating some synthetic data, like, the challenge with synthetic data sometimes is there's a model in between the raw data and what you consume. So if the model has kind of a bit of a mismatch associated with the underlying properties of the data, you can lose some information. But it's a fairly accessible way if somebody is familiar with, sklearn or some of the kind of local normal data science tools. It's a fairly accessible way to be participating in the competition, to pull down some synthetic data and then to try to explore it with the tools that you're most familiar with. And then from that, obviously, just making predictions the way you would in a calc competition. Now, of course, you can go much, because some of these things like SQL queries kind of aggregate together different OpenDP pipelines, etc. So there's a higher level of granularity, I guess, if you were to go into some of the OpenDP. But if you just want to participate, but maybe you don't want to go down that rabbit hole too far, pulling some synthetic data or even SQL queries can be a good way to get started. Now, for people who are quite familiar with sklearn, I think our next speaker might be might feel like things that you're very familiar with, because it's Nisha Houlihan, who's from IBM Research, who wrote Diffprivlib, and that very much mimics the functionality of some of the sklearn interface. So if you're familiar with like random forests, decision trees, just regressions, I'm going to let you take over now, Nisha. Then that might be a tooling that you can take advantage of in your participation in the competition. So over to you, Nisha. Cheers.
Cool. Thank you very much, Jack. I'm just going to do the honors and share my screen there. So what I want to do here is start with a few slides on, I guess, the motivation around actually building Diffprivlib in the first place. And, being a research scientist, I have to start with a few slides before we go into a demo. And then I'll run through a few notebooks on, Diffprivlib in action and how you can use it as part of the competition. This is meant to be, or I'm going to give this talk as a standalone kind of how Diffprivlib works. And then you can figure out how to mold this into the competition format with the starter code that you'll be given. So let me see now. I'm going to continue assuming that you can see my screen. If you can't, just shout me, Jack.
That's perfect.
So cool. So Diffprivlib has been around since 2019. Hang on a second, we're missing some text over on the right. And I guess at the time, differential privacy was 13 years old, and there was an awful lot of literature out there covering machine learning with differential privacy for a whole heap of algorithms. I think at the time there was already differentially private deep learning capabilities and libraries out there, but there was nothing for running machine learning algorithms, or I guess running them very easily. There was a lot of code out there in the wild, spread across loads of different repos in loads of different languages, running loads of different models and algorithms, but there was no standalone library that you could run a few different machine learning algorithms with, or different code like that. So our goal with Diffprivlib was to build something that was user-friendly and that people were kind of familiar with before they even knew it existed. And for that, we use the Python programming language, which is very popular in the machine learning and data analytics space. And we use NumPy and scikit-learn as the foundation tool for our library. And I'd consider them the de facto standards for, I guess, low-level data analytics and for traditional machine learning. And our goal with Diffprivlib was to give a virtually identical user experience to NumPy and scikit-learn, and using a lot of default settings for the privacy parameters of Diffprivlib, that people would be able to run it as they would have done for NumPy and scikit-learn, so that people would be familiar with the library before they even used it. And I think from a lot of feedback we've gotten, I think by and large we've managed to achieve that. So this is a very brief snippet of code showing how we would train and use a Gaussian naive Bayes classifier from Diffprivlib. So anybody who's used scikit-learn in the past would hopefully be familiar with this kind of syntax. So we initialize our naive Bayes classifier with some extra parameters here for the differential privacy component. We train it or fit it using the fit method and fitting our to the training data set that we've provided. Then we can classify unseen examples using the predict method, as you would with scikit-learn. And then we can score our classifier using the score function. So the idea with differentially private machine learning is that we're achieving differential privacy on this trained classifier, so the CLF variable, with respect to the training data set. So the idea is that if you fit this Gaussian naive Bayes classifier and then, for example, pickle it and send it off to one of your friends or to another company or another data scientist, that they won't be able to reverse engineer the original training data set, or that they won't be able to infer some private attributes of an individual in that training set, because differential privacy has been implemented here. So you can use Diffprivlib for data exploration and data analytics. You can see here we're plotting some nice bar charts and grids. All of these have been executed with differential privacy guarantees. These are very good because classical statistics, as I would call them, are very well understood, and we can hit our differential privacy guarantee exactly in a lot of cases. So histograms are a good example that we can hit the epsilon that we have. We can hit that perfectly, whereby the less than or equals in the differential privacy equation becomes an equals to, which is very good. So these tools are very useful for exploring and understanding data without having explicit access to the data. So you can see here we can plot various characteristics of the data set. And obviously then in a data science pipeline, you can manage the data risk and the privacy risk with this. Then we also, in terms of this scikit-learn aspect of it, then we have a lot of classical machine learning algorithms that we can run. These algorithms, again, are very well understood, and we can, again, hit the privacy guarantee fairly well in a lot of cases. In terms of the capabilities within Diffprivlib, we have models for pre-processing, for dimensionality reduction, for classification, regression, and clustering. The one caveat, I guess, I'll give here is that all of our algorithms here are run with pure epsilon differential privacy. In other words, we've got no delta. The trade-off for that is that it works best in lower dimensions. Now, we do have dimensionality reduction, as we say here, so you can project your data into lower dimensions to work well, and you can do that with differential privacy as well. We have 4 main modules in Diffprivlib, and I'll just run through them quickly now. So the first is the mechanisms module. You might not be using this as part of the competition, but it's important to know it exists all the same. So the mechanisms are the fundamental building blocks of differential privacy, and they're the bits that we actually use to add noise to satisfy differential privacy. So all of the models, all of the scikit-learn models, and all of the NumPy tools use a mechanism under the hood to add noise. And you can actually experiment with them in a Jupyter notebook by yourself, just seeing what the distributions are and how they behave. And there are examples here. We've got various different mechanisms for various different data types. And again, a common syntax. So you initialize your mechanism and then you randomize a particular input using the randomize function, and randomize with an S as opposed to a Z here. Next, we have the models module, which is the scikit-learn part of Diffprivlib. So all these train a particular machine learning model with differential privacy built in. Again, we use a mechanism or mechanisms under the hood to achieve differential privacy. And all the models inherit the scikit-learn equivalent as its parent class, which should make it a bit easier to use it in kind of downstream tasks that you would have used a naive scikit-learn model before. There are circumstances where you might be thrown a specific Diffprivlib warning, for example, a privacy leak warning, and I'll give more details on that in the next slide. And compared to scikit-learn, some functionality is a bit limited because we have to play to the, play to the literature that has done the research on this, which limits us in some aspects, but that's not a big blocker in most cases. The second last module then is the tools module, and these are a suite of NumPy functions that we can use to, again, explore data and get some statistics on data. Again, we use mechanism or mechanisms under the hood to achieve differential privacy. And again, we might require some extra parameters or hyperparameters to correctly calibrate the differential privacy part that you mightn't have needed for a NumPy function. And finally, then we have our accountant module, which is a budget accountant that tracks the epsilon spend that you're giving or that you're using across for example, across a script. So yeah, in this case here is just the budget accountant class that you're initializing, and you can then, that keeps track of the epsilon spend across various Diffprivlib calls. That's especially useful when you've got a lot of queries that you're executing. And that allows you to also add a non-zero slack, so we can introduce a delta in the accounting phase to reduce the overall epsilon spend. So I think that is the end of the brief slideshow. So I'm going to next show the GitHub repository where where Diffprivlib resides. So we're on the IBM domain in GitHub. If you search for Diffprivlib, this will hopefully be the first result that you get. So this will be your first port of call. There are instructions on the README onto how to install Diffprivlib here. So just pip install Diffprivlib. There's an example of Diffprivlib in action. And then also importantly, we have our documentation here at Read the Docs. All of the notebooks that I'm going to show you here are in the notebooks directory on the GitHub, and you can take a look at them there. Notebook Viewer is a little bit handier to view the notebooks than on GitHub, so I'd recommend using that instead. And I'll run into some examples so straight away. So this is the getting started with Diffprivlib and using differential privacy for machine learning. I call it getting started in 30 seconds. If you want, you can try it out and see if you can get through it all in 30 seconds, but I'll take a little bit longer than that now. So the first thing we're going to do is we're going to import a data set, so the classic iris data set. And we're going to do a train test split. So we're going to randomly split the data between train examples and test examples. And then what we're going to do is we're going to import the Gaussian naive Bayes classifier from Diffprivlib. So that's in the models module. We're going to initialize it and train it with the training data set that we've just imported. Now, immediately you can see here we're getting a privacy leak warning. And that's because we haven't told the model the domain of the data. In other words, where the data resides within this, within the domain. Now, this presents a problem because we can't initialize our mechanism with the right domain of data or how varied the data is. So in this case, what the model does is it actually reads the bounds of the data from the data itself. And anybody with a background in differential privacy or in privacy enhancing technologies will know that this is not a good thing to do because you're leaking privacy in this case. So this is not something that we would want to do in the future. Typically, you would choose your bounds based on domain knowledge or background knowledge based on the data. This could also be included as metadata of the data set, or you might also be provided with for example, a public or non-sensitive version or copy of the data set that will allow you to infer the bounds of the data set. So here what we've done is we've trained our naive Bayes classifier, which allows us to use it to classify unseen examples. And you can see here we're predicting various labels for this test data set. And down here then what we've done is we've selected a range of epsilons from 10 to the -2 to 10 to the 2 and trained lots of different classifiers at these epsilons and plotted their accuracy. And as you would expect, the accuracy increases as we increase our epsilon or increase our privacy loss. So that is the first example. I'll move on to the second of 3 examples then, which is a bit more, a bit longer, but we'll get through it all the same. So here we're going to use the adult data set using only the numeric columns in the data set, and then taking our label as well as our Y values. Now the adult data set already has a train and a test split done. Don't have to do that in this case. So we're also going to import the test data set. And in this case, the first thing I'm going to do is train a classifier without any differential privacy. So logistic regression here is the default scikit-learn logistic regression classifier. So we're going to use that as a baseline for our data and for our model to see how it performs. We're specifying a particular parameter here for the scikit-learn version so that it is a direct comparison to our Diffprivlib version, because we do use the LBFGS solver in Diffprivlib. We can see that we get a non-private accuracy of 81% in this case. So you would expect that if we train a differentially private classifier, we're probably not going to be able to do better than that, because that's the baseline that the data is giving. And in this case, we're going to train our differentially private logistic regression classifier here. I'm passing a random state integer to just give us a bit more reproducible results. And again, because I'm not telling the algorithm the range of the data or the bounds of the data, then it has to go into the data and read that, which again gives us a privacy leak warning. And one other thing then is the default value for all epsilons in Diffprivlib is set at 1. So if you don't specify an epsilon for our logistic regression classifier here, then it's going to assume that you want an epsilon of 1, and it's going to train the algorithm with that. And in this case, after training it with epsilon of 1 and with the privacy leak warning, we get a test accuracy of very nearly 80%, which compares quite favorably with our non-private accuracy up here. Now, one important part of Diffprivlib was that we wanted what in some cases is called epsilon consistency, where as you increase epsilon towards infinity, that you get closer and closer to our non-private accuracy. So all Diffprivlib models can accept an epsilon of infinity, and in some, other than some exceptions, you should get the same accuracy as you would get with the vanilla scikit-learn version. And in this example here, we're getting 100% agreement on the test data set between the non-private scikit-learn version and the Diffprivlib with epsilon equals infinity version, which is a good sanity check for this case. And then last but not least, we're going to run our logistic regression across a range of epsilons from 10 to the minus 3 to 10 to the 1. And this is the accuracy that we get back. Now you're wondering, okay, why is that line below the non-private accuracy line that we showed previously? And that's because of some clipping that's done on based on the norm of the data. And that's just a kind of an artifact of the model in this case. If we want to increase our data norm here, we would hit our non-private accuracy there. But again, that's a trade-off between the amount of noise you're adding, noise increases with a larger data norm, and the bias that you introduce by clipping more. And I'll just draw your attention to one thing here, which is that we're flatlining on our accuracy at about 10 to the 0, so epsilon equals 1. And just to bear that in mind for the last notebook I'm going to show for 2 minutes before I run out of time. So all the stuff at the start is the same. We're importing our data set. And in this case, we're actually going to train a pipeline of different models to, first of all, to scale our data to uniform variance and zero mean. Then we're going to do some dimensionality reduction to two-dimensional data set using PCA. And then we're going to train a logistic regression classifier on that two-dimensional data. In the non-private case, we're seeing a very slight reduction in accuracy. So I think the previous notebook showed that it was 81% accuracy, and here we're 80% accuracy. And what we're going to do here then is we're going to combine various Diffprivlib equivalents. So here we had scikit-learn equivalents for standard scalar, PCA, and logistic regression. And down here, we're going to use the differentially private versions of those, parameterized accordingly with bounds, data norm, and data norm. And you can see here, again, the default is epsilon equals 1 for each of the 3 components, which gives us a total epsilon of 3. And we're getting a baseline accuracy here of 79%, which again compares very favorably with the non-private version. And last but not least, if we run this classification for a range of epsilons, I'm not going to run it live because it takes a bit of time, but this is one I baked earlier, I guess you could say. And you can see here that we're actually approaching our baseline privacy at less than 10 to the minus 1. So in this case, even though we're training 3 different models at each epsilon and combining the epsilons together, we're still better off because the scaling, the dimensionality reduction, and then the training of the model allows us to fine-tune the noise addition much better than training on the data out of the box. So that's something to bear in mind as part of the competition, especially. So I'm at 5 to now, so I'm going to leave it there. If there's any questions, I think we might be doing a Q&A, or there are ways to get questions to me later on anyway, but hopefully that was somewhat understandable.
That was great, Nisha. And there was a few questions that came in actually, so I think you can probably stay on. So the first question that came in was basically whether or not both the training and testing was differentially private. Now, I think the understanding of that is it's actually the training mechanism itself. So the queries are like working out a gradient in order to train a machine learning model. So predictions have no noise is added onto predictions that are passed through the model. It's during that training stage. Anything you want to kind of add to that, Nisha, or comment?
Yeah, I guess it goes back again to wanting to export the trained classifier, and it's the parameters that are trained. So in the context of naive Bayes, it's the means and variances that you learn. That's what's differentially private. We don't actually want to achieve differential privacy on the test data set, because that's the value that's there, is how can we turn a test data set into labels, and that's what we want to be accurate, but it's with respect to the training data set that we achieve DP.
Mm-hmm. And in the competition itself, if you make let's say a Diffprivlib pipeline, so you want to do PCA and then run a random forest and then something else, you can just pass up that pipeline. It gets deserialized, sent, unserialized, run, etc. But you will get back the model, so you could just apply it directly on your test data if you want to. One thing I will say is, Nisha said, yeah, put the epsilons as infinity, that it will run. So we will catch that and we check if you obviously exceeded the budget, obviously, for the entire competition. So if you pass more than 100%, then you can't get a result. So that's just a limitation in case anyone's trying to be cheeky. Another question which we answered in the chat was just if the code was available. So I shared the link to the notebooks in the Diffprivlib GitHub repository. But what we'll do is this week, actually, we're going to bring together lots of the examples that you saw here today in the notebooks, just in plain form, and then how you execute them in the competition. So you just literally see, it's almost the exact same, but you just say, hey, execute this for me, and then you get back your result, and you continue your workflow. So you'll see that, and hopefully it explains all of the concepts and shows you how to use some of the tools. And I think the last question that came up was from Matt. So if we do the same analysis on increasing epsilon, as has been done in the demos, does it cost max epsilon or some epsilon? So very good question. You mean in the competition setting or in general? In the competition setting, we're currently not saving the current state of a model. In the competition. So we're not currently saving and storing the state of the model as intermediate steps. So it will count as sum of, as opposed to max. However, what we do say is, say you've used epsilon equal to 5, delta equal to 0.001 or something at time t, and then you make a submission. Your score is going to be your accuracy at that point in time minus the loss function from those two. But if you ask for more epsilon and delta later on, but your highest score was at that time t equals 1 or whatever, you don't get further it's your max overall score that's kept. So you can be a little bit more aggressive with your epsilon and deltas towards the end, knowing that that's not going to upset any of your previous scores. Nisha, out of curiosity, in more of a general setting, do you allow for is it called hot restarts when you train based on when a model's already trained and then you train it again for longer by adding more epsilon or not?
Yeah, so that's a bit of a sticking point for us because scikit-learn allows kind of hot restarts, as you say, or warm restarts. So we mirror what scikit-learn does. So one example is with naive Bayes. If you train a differential private naive Bayes on a data set and then do another partial fit on the same data set, then the epsilon isn't increased. And I guess the reason for that is if you were, or at least that's my understanding, I might be incorrect, I might be doing something fancy in the background. But for example, if you were to run a naive Bayes on one data set and then retrain it or do a partial fit or a warm start on a different data set, then the epsilon would be the same because you're running it over a partition effectively. So the overall epsilon would be still the initial epsilon that you asked for. So I guess there's reason for doing it like that.
Yeah, sure. So in this sense of, like, say we were training something where you're using some sort of gradient method, logistic regression. So you work out the gradient and then you take a step, you know, et cetera, et cetera. Presumably at each step of that, some epsilon is used. Is that correct? So if you were to run it on the same data set twice, it might not account for it, but you might actually be doubling your epsilon.
So we actually don't use gradient descent for logistic regression in Diffprivlib.
Okay.
So I'm not going to venture a guess on that one.
Sure. Maybe next year, if we're running this again, we can include other frameworks like Opicus and stuff like that for, like, I think it's a Tiana DP framework, and hopefully we can pull in a speaker from there and hear what they do as well, and, you know, also use this as a bit of a knowledge share across the different frameworks and libraries. Great. Well, it doesn't look like there's any more questions now. Anyone can ask a question later on Discord. Someone asked one last week for Nisha after the call, so I WhatsApped him and got an answer. But feel free to ask any more questions. And a recording of this webinar will be up on the Big Data, UN Big Data YouTube channel, probably likely today. It's not me who does it, so maybe it's today or tomorrow. And we'll share that as well on the Discord page and share links with everyone in case you missed any part of it. But thanks to everyone for joining. Thanks very much to the speakers. So Anisha, Josh, Michael, Arvind, etc. And looking forward to seeing you all in the competitions. And please do ask any questions on Discord, and we'll have all that starter code up kind of in the coming days. So try it out if you get stuck. That's literally why there's people on Discord to be there to help like take you out. So thanks very much, and we'll see you all shortly. Thanks, guys.